So, welcome to your second video for the grade 8 year. From what I was able to gain, there's still some understanding of force and even using the spring scales. So I'm going to put a lot of information into this video just so that we're able to get through the information that we already know so we can go and move on and further build your understanding of force. So, the reason why we had the last lesson was to understand and be comfortable with the word interaction. When you imagine a force, I don't ever want it to be a one-sided thing. You can't have one thing when we're talking about force. Whenever you're imagining a push or a pull, there's more than one thing involved, even if that thing is a non-contact force, such as gravity. Okay? So, never think that a force acts on its own. There's always something else that it's interacting with. And I mean, if you really were to think about it, do you ever imagine a push or a pull with just one thing and nothing else interacting with it? You don't. So I just want to make sure that that misconception is gone. Interaction is required for force. Now, Sir Isaac Newton is basically the man who came up with all of the relationships between matter, motion, and force that we build our knowledge upon today. And we go by his 3 laws of motion. And so I'm going to go through those with you word for word and then kind of explain what they mean. So every object persists in the state of rest or uniform motion, which means it's not moving, or it's going in a straight line at a consistent speed, unless it's compelled to change that state by forces impressed on it. So everything in motion wants to stay in motion in a straight line until another force acts upon it. So on Earth we have gravity, we have friction, we have drag, all things that would cause an item or object to decelerate. If we were in space in an infinite vacuum and we push something, it's forever going to go into a straight line until another force acts upon it. Then it starts, more than likely, gravity going towards something that's a larger object, or it hits something like an asteroid and stops itself because it puts an equal force on both sides. But for the next one, force is equal to the change in momentum, and mv means mass times velocity per change in time. We're not going to go over that first one right now. You would need to understand changing in speed and changing in mass to really dig deep into that, which you're going to do in physics later on. For constant mass, force equals mass times acceleration. Okay? So as long as your mass stays the same, force is the mass multiplied by the acceleration. And you can think about it this way. If you accelerate slow, same amount of mass, it's going to be pretty easy to stop. The faster something moves, the harder it's going to be to stop, okay? Because the force is greater. Now, for this one, for every action, there's an equal or opposite reaction, which means if one thing runs into another thing, it's pushing or applying its force that way. And that's the Newton's cradle is about. And the Newton's cradle is the thing with 5 marbles that if you put 2 up on one side, 2 come up on the other side, because it is an equal reaction in the opposite direction. All right, if this seems really interesting to you and something you want to further study, I would recommend you look up the laws of thermodynamics, because then that starts to go into energy conservation and being able to create something with its own sustaining energy. And right now it doesn't seem like that would work. There's a few different theories of how it could, but the energy transfer is always there. So the main thing we're going to focus on is Newton's second law. All right, and here's how I'm going to want you to think about it. So a net force upon a mass accelerates that mass. What that means is the net force is greater or less than 0. When that happens, your mass then moves. And it moves at different speeds depending on the amount of force that's acting upon it. So, any number of forces of different magnitudes can act on a mass simultaneously. So we see a lot of diagrams where there's one arrow or there's two arrows, but realistically there's forces going on several different sides of masses all the time, more like this picture here. Now if you were to look at it, you can see the top right arrow would be the largest, right? So in this instance, it's going to start turning like this, because it's pushing that corner over and forcing it to go that way, as the forces here and here are too little to make that happen. But then the force that's going up here like this is helping that motion. Okay? So, a little bit harder to understand, but forces are an essential part of physics and an essential part of understanding machines and the reasons why we have them. So, acting on a mass. So, one force acting on a stationary mass is going to make it move. That's the most simple thing that we see, right? So F being the force, M being the mass, the force will take and move the mass, right? Easy enough. But now multiple forces acting on a mass simultaneously. This is what I want you guys to start imagining. So now we have a force acting on a mass, and I'm going to call, in this case, the negative force, or the force acting against it. So the force pushes the mass. The other force is either not pushing the mass as much or pushing the mass enough to make the net force equal 0. Okay? Net force. So this is the equation. When we look at science, I like to see it as basically cores, like the Earth. Math is in the center. Okay? Math is the center of, I can see all the sciences as. Then there's physics. Physics is the understanding of the forces in the world and energy. And a lot of those are done by calculations because we can't see them. Then there's chemistry. Chemistry starts going into molecules and different chemicals. And there's biochemistry, which is more of the natural world. Chemistry as it exists in the natural world. Then biology, the study of living things. None of those can exist without math in the center. So I'm going over that right now with you. So this looks a little bit complicated. So F net would represent the net force. And the net force is adding all of the forces that are interacting on it. And remember, some of these forces would be positive and some would be negative. So, for example, F1, F2, so force 1, force 2, force 3, force blah, 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 blah. Fn would represent the amount of force, the amount of forces we're counting, and that would be the last one. So it can fill up, it could be a long equation, it could be a short equation. For now, I just want you to analyze something like this. So the net force is going to be measured in newtons, because newtons is the units that we talk about, or are the units that we talk about when we're talking about force. So we have 5 newtons going in one direction, negative 5 newtons going in another direction, therefore the net force is 0. If the net force is 0, it's not moving. If this equation changes, if either side of the equation change, then the object is in motion. Right? So yeah, when it's anything besides 0, it's going to move. Even if it's a very, very small amount, if that is unbalanced, it will move. Okay? When force is used to make an object move, energy transfers from the object in the form of kinetic energy. And I'm going to ask you guys in class if you understand the term kinetic energy, because that's going to be a big part of our next lesson. So kinetic energy is the energy that's transferred to motion. It's transferred to something called potential energy, which is stored energy that then gets changed into motion energy. If you have any questions for me, feel free to leave them in a comment on the Google Classroom, and I'll try to get them answered as soon as possible. If not, go ahead and bring those questions to class. We can have them in the moment of science or while we're doing our lesson. So hopefully this was informative. If you need anything else and you can't contact me on Google Classroom, feel free to send me an email as well. Thank you, students of science. Have a wonderful day or night.